one thing further that we can do, hopefully without beating this to death, is why do we care about fin temperature? Like, if you're actually a thermal engineer, under which circumstance would anybody ask you, what's the temperature at L over 2? Like, people really don't care that much about the temperature of fins. What you care about is how much heat you're sinking into the fin. So we have a temperature expression. Let's go one more step and figure out what the heat transfer is from the fin, and then whether we can come up with like simplifications that let us quickly assess this stuff, which we'll get through the fin efficiency. Okay, so let's take our expression we have here. If we're going to compute the heat flow through the fin, we need to look at what? We need to take a control volume. So I'm going to draw us a control volume around the entire fin. I want to know how much heat is being lost from that control volume. So what are the ways that I could go about doing this? There's basically two ways. How could I make an assessment of the total heat loss from the fin, knowing the temperature?
Considering like a control volume and then integrating it over the line?
Yes. So that would be option 1, or we'll call that option 2, but we'll say Q dot fin is equal to what? It's the integral from 0 to L of h bar perimeter T minus T infinity dx. So I could take my temperature expression and I could integrate that and get some solution. That's a valid way to do this. It's also kind of a pain in the ass to do. So what you want to do instead is let's look at just this boundary here. So if I can calculate the heat that's crossing that boundary, that is the heat that's being lost to the fin. So option 1, which is our preferred option in most cases, would be to say Q dot fin is equal to minus K AC dt dx evaluated at x equals 0. Right, that's kind of an easier thing to get to once you have this temperature expression. So, okay, let's do that. Let's plug this in. We have Q dot fin is equal to minus K AC times d dx of this temperature, so T infinity plus TB minus T infinity cosh m times x. I'm running out of room, so minus TB minus T infinity tanh of ml sinh of mx. All of that evaluated at x equals 0. Okay, that's just the expression for Fourier's law with our solution plugged in. Going through and taking that derivative, evaluating at x equals 0 gives us the following. So I'll just skip the plugging in zeros and taking derivative. We end up with Q dot fin is equal to K AC TB minus T infinity tanh of ml times m. And again, remember that m is equal to square root of perimeter times h bar over k AC. All right, so that's our expression. So now you can just evaluate this and get back the heat sink to the fin. Right, so that's pretty easy. You have all that information, all that geometric information you have. So Q dot fin, okay, that's great. We can also calculate something called a fin efficiency from this. A fin efficiency is, let's imagine a scenario where the conductivity of this metal in here is basically infinite. Right? So that's the case where ML is really small. In that scenario, what is the temperature of the fin going to be? TB, entirely, right? So in that scenario, you're basically using all of the area of the fin at its maximum possible temperature. That's the maximum or the upper limit on heat transfer from this fin geometry. So fin efficiency just says, okay, eta fin is just the actual heat transfer q dot fin over q dot max. Right, where q dot fin is that expression up there, and q dot max is that maximum value. So let's do this. So that would be q dot fin over h bar times AS, the surface area of the fin, times TB minus T infinity. Again, this is making the assumption the entire thing is at TB, which is our maximum heat transfer. Let's bring in our original expression and rewrite this. So eta fin is equal to, what I'm going to do is take this m that's over here, which involves k and AC, and I'm going to combine it with these, and you get this kind of square root term that multiplies everything. So we end up with square root of k AC h bar perimeter times TB minus T infinity times tanh of ML. Right, that is the exact same equation as above, just integrating the m part in. And then divide this by our maximum h bar AS TB minus T infinity. So what do we first of all notice? TB minus T infinity goes away. So what is that saying? That's saying the performance of my fin in no way depends on the temperature. Right? Heat transfer from the fin depends on the temperature in absolute units, but the efficiency, the amount of the fin that's used for heat transfer, is another way of thinking of that, does not depend on the temperatures, which is kind of surprising, right? But the math tells us that is true. Right? So we go through this whole process, and you can simplify all this down. One more step, eta fin is equal to tanh of ML divided by ML. Right? For this geometry, constant cross-section area, constant or known temperature at the base, adiabatic tip, that's your fin efficiency. Right? We can write the fin efficiency into like a resistance equation. So let's look again at this, this plot. Let's see. Actually, what I'm going to do is, we're a little short on time, so I'm going to skip. I just want to show you, I'll show you this first of all. So the fin efficiency is our equation up there for this geometry, these assumptions. If you know ML, you can predict the fin efficiency just by computing it this way, right? So it's saying if I have a ML in this range of less than 1, most of my area is being used for heat transfer. As you start getting further and further out, basically you're just buying extra material and you're not using it. Like the fin is not effectively using the area that's there. You can look up this stuff in ease to some degree. So if you go into ease, pull up the thermal, like the options menu, and then like the property lookup dialog, and go to fin efficiency. It'll give you a bunch of different geometries. And what it's going to give you are things like fin efficiency if you tell it what ML is. So you compute ML for your geometry, and then you get back the performance. Some of these shapes are kind of weird. Like, why would somebody build these decreasing area shapes? Well, it turns out, like as you go further along, you have less heat to conduct. So the less heat you have to conduct, the less cross-sectional area you need. So people have devised this idea, like let's make the fins tapered, and that gives you pretty much the same performance, but saves you on buying material, right? So it's just a cost-saving measure. But okay, so this stuff is in ease. I think that's probably a good place to wrap up, and then we'll finish our discussion of extended surfaces next time on Monday, and then move on to 2D problems. Thanks.